Hi, I'm George Crump with VergeIO. Today we're going to talk about vSANs and addressing vSAN performance. A lot of times I talk to customers and they're not crazy about the idea of a vSAN because they've had some bad past experiences. They're concerned about performance and scalability, all very valid things, despite the fact that vSANs should be a lot less expensive because we're just using server class SSDs and hard disk drives. So let's talk about some of the things that VergeIO has done to address some of these performance issues. So let's just do a quick refresher on what exactly a vSAN is. So what we're typically going to try to do with a vSAN environment is we're going to take a server. We're going to throw, of course, we'll have some CPUs in that server. And then some storage in that server. I've got an SSD here. And what we're going to do is basically take this and create a logical SAN out of that. First of all, I'm going to need more than a couple in there. So let's put a few in here. And then we're going to want more than one of these, obviously. In most environments, you need at least 3 nodes to be able to pull together a good vSAN. Our environment, we could actually do with 2, but I'm going to go ahead and do 3 right now for that purpose. Now, the idea is we're going to essentially aggregate the storage that's inside of these servers and create a virtual volume out of that. It's a great idea. We've got 10 gig Ethernet now. Performance should be fine. All those sort of things should be working for us. Except again, there's this concern, and I think it's very valid. So let's dissect what some of the challenges are. First of all, the way VMware and others do it, I'm not necessarily just picking on VMware here, but they're probably the most relevant, is they're going to run vSAN down here. And that vSAN is essentially a VM that is going to provide all the storage services. And then it is going to connect to, of course, the hypervisor, which in this case is ESXi. Right? Now, and this becomes the problem because the storage is essentially a second-class citizen to ESXi. We don't get the same level of performance and priorities and all those things we sort of need to be able to pull this together. Also, remember that ESXi is essentially the OS. It's booting Linux, of course, but what's really happening here is I'm sort of provisioning storage, giving it the vSAN, and then vSAN is giving it back to ESXi. So you've got a lot of overhead here. Now, the other challenge when we do this aggregation like this, and data is being written to this virtual volume, of course, it's essentially being written across these 3 servers. There's a lot of what we call east-west or internode communication happening here. And so that becomes part of the problem as well. The other challenge is as you grow this environment, if you want to just, you have to basically grow the same or add the same nodes over and over again. And that's fine if you need a balance, if you happen to have a balanced environment. But what if you have a situation where you've got plenty of capacity or plenty of CPU performance, or you just need one of those 2 attributes? Well, that becomes a problem because you can't split that up. And so what ends up happening is in most customer environments, you end up what I call out of balance on your environment, where you either have too much storage or too much compute. In my experience, it's almost always too much compute. So that becomes a challenge as well. And so all of this really adds up to a little bit of a challenge for customers. And so we specifically set out to fix these issues by creating our product. And so what we did that's fundamentally different is we started with VergeFS, which is our storage software, written from scratch by us. However, instead of making it a VM of, we injected it into the hypervisor, which we refer to as Verge HV. Okay. We use KVM and QEMU, integrate directly into that, essentially forked those two. Then the other thing we have is Verge Fabric, and it plays a role in our internode connectivity and performance. Although primary claim to fame is that it can provide firewall routing, BGP, all the different things that customers want in a software-defined network. Now, what's different though is this is a single piece of code. The storage software is not a second-class citizen to the hypervisor, and we call that VergeOS. Okay, and so now what happens when I bring my server in? The storage software has direct access to the storage itself, and it's also sharing everything with the hypervisor. So again, I'll put my CPUs back in. And we'll put our storage back in. And this gives us similar configuration, except again, remember everything is now shared within the same core software. So if we come back out here, now this gives me some interesting capabilities. So first of all, of course, I'll build out an environment. We can do to this the same things that we would do to other environments. So we could start with 2 nodes instead of having to force you to 3. Most of our customers at least start at 3. We can go from there. Now, one of the things that's unique though is, let's say I do have that situation. Let's say I have plenty of capacity, I just need more compute. Well, with our environment, we can bring that in. We can maybe scale this up a little bit and put some additional processors in it. And just a boot drive. And that's a perfectly valid configuration in our environment. And so we could bring this into the existing environment, and there's no problem at all with doing that. Now, the other thing, I talked about how we manage storage and deduplication and things like that on a prior video. I'll link to it in the description. But one of the things I want to talk about is our connectivity. So when you connect these nodes, we're typically going to recommend 10 gig connections, although of course we'll support faster. The protocol though is native to us. It's our custom protocol, and it talks natively to the ports. You don't have to do link aggregation or anything like that for port bonding. We're talking natively to port. We're managing the balancing of that traffic across those two ports or 4 ports, whatever it is. For example, if you did put a quad port 10 gig or 25 gig Ethernet card in these servers, we'd use all 4 ports and we'd use them perfectly distributed across the environment. Great for redundancy and really, really high performance environments. So this really helps storage IO traffic significantly. We talked about in another video, I talked about deduplication. Again, a core thing is deduplication is running here. And so what happens if I come in and I bring in a new piece of data, I am going to assign that data to one of these nodes. And then that node is going to process that data. Of course, in a virtualized environment, there's a good chance I'm going to find redundancy just on operating systems alone. And so when I do that, I'm going to mark these redundant segments and just update metadata. I don't have to do anything else. Well, because dedupe is running here and not on the storage, I don't have to transfer the whole payload and have the dedupe happen down there. It's actually happening at the hypervisor level. So I essentially have a hypervisor and network aware environment. So these redundant segments here, once I update metadata, I don't touch another network segment. I don't touch CPU. I don't touch anything. So it's very, very performant from that perspective as well. The other thing to understand is because we're running here, both the storage services and the hypervisor have equal visibility into the RAM. And so we know exactly how much RAM to allocate to those environments. So very powerful from that perspective. Also, the RAM is essentially deduplicated. So I get more value out of my cache from that standpoint. So I'm much, much more efficient at RAM utilization, and I can use it more constructively. Okay. The last thing is, let's talk about these unique segments here. When I write those, as I've kind of mentioned in other videos, what I'm going to do is I'm going to write each one to a different drive on a different node or server, like this. And so I get perfect data distribution. Again, it's a synchronous replication. So very, very fast, not a lot of overhead to it. If there's a drive failure, no performance loss there. I can rebuild very, very quickly because I don't have to run everything through another algorithm, things of that nature. So the data distribution, though, that I'm doing here also helps from a performance standpoint, because now I'm using multiple network segments. I'm using multiple CPUs. So I get this wide distribution of resources that I'm fully able to take advantage of. So these are just some of the reasons. Obviously, there's just basically core coding that we think we've done better, but a very fast network, custom network protocol designed for us. The fact that the storage software runs as a equal citizen to the hypervisor, not a subordinate to it. The third is the data protection scheme helps both eliminate processor overhead in managing data protection, and it also helps us leverage multiple CPUs and segments for that. And then also the deduplication being integrated into the whole process makes everything more efficient. The network, the CPUs, the RAM, everything just benefits as a result of that, which you don't get to see in other environments. So as a result of that, you'll see a storage environment that can use commodity SSDs today. As I recorded this video, 4 terabyte NVMe SSDs are about $1,000. So very affordable, very scalable, and allows you to develop a highly competitive priced but very high performance that will outdo an iSCSI and an NFS array, and at least go toe-to-toe with an expensive fiber channel array. So that's how all that works. So this is why the performance works. Again, I'll put links into some of the deduplication and other videos we've done in the past. Thanks for watching. I'm George Crump.